All right, so for this first problem, I'm just going to think about what kind of motion we see here with this graph. So initially, right there, a horizontal line on a velocity graph indicates constant velocity, constant positive velocity because we are above the x-axis here. So that's the first motion I see, and then the second motion here, what we see is as that graph approaches the x-axis, it's slowing down, and so this is going to be a case of slowing down with a positive velocity and a negative acceleration. So in order to draw this dot diagram, I want to show constant positive velocity, which means going to the right, as it tells us up here with our sign convention. And so I'm going to have my dots evenly spaced initially, going to the right. And then I'm going to begin to show slowing down, so the dots are going to get closer and closer together, like that. When I go to draw my vectors, initially at T1, which is down here, okay, it's going to be a case of positive velocity because it's going to the right above the axis, therefore it's positive, and since it's constant, my acceleration is 0. For the second part, I still have a positive velocity, so still going to the right, but I'm slowing down, which means my acceleration must be in the opposite direction to the left. All right, moving on to the next question here, we're dealing with the situation where an object's accelerating, so I'm going to go ahead and set up my variables for acceleration like I have right here. And so let's go ahead and read our problem and get whatever variables we can. So we're told that Jake is initially driving at a speed of 15 meters per second. That's going to be my initial velocity here. And then he slows down with an acceleration of 3.5 meters per second squared. So that tells me two things. One, my acceleration is 3.5 meters per second squared, and the fact that he's slowing down means my acceleration is opposite my velocity, so I'm going to make it negative. First question says, how fast will I be traveling after 2 seconds? So I'll put that in as my time. And then I'm going to use my acceleration formula, Vf minus Vi over t. So I have negative 3.5 is equal to Vf minus 15 over 2. I'm going to multiply both sides here by 2 to get rid of that 2 on the bottom. And so what I end up getting is negative 7 equals Vf minus 15. I'm going to go ahead and add 15 to both sides of the equation here, and I end up with Vf is equal to 8 meters per second. For the second question, I now want to know what is the total amount of time that it will take for Jake to come to a complete stop. And so I go ahead and start setting that up again. My acceleration is going to be the same, negative 3.5 meters per second squared. I now don't know my time anymore. That's what I'm looking for. 2 seconds took us down to 8 meters per second. What we want, though, is that total time it will take to come to a stop. So I don't know that. I do know my VI is still 15. And because I'm coming to a stop here, that means my Vf is going to be 0. So I'm going to set up the same equation here. Acceleration is Vf minus Vi over t. So I have negative 3.5 is going to be 0 over minus 15 over t now. So negative 3.5 is equal to negative 15 over t. What I would do here mathematically, because we have that variable on the bottom, that t on the bottom, I'm going to put this over 1 and cross multiply. And so what I end up getting from that is negative 3.5t equals negative 15. We divide both sides by that 3.5, and I end up getting that my time here is going to be 4.29 seconds. All right, moving on to this problem here with Jonathan. We're told that Jonathan walks this path here, 30 meters west and 90 meters south, in a time of 50 seconds. And the first thing we want to do here is determine what Jonathan's average speed is. So with average speed, I'm going to go ahead and set up the following things, thinking about speed, distance, and time. I know my distance is going to be 30 plus 90, or 120 meters. The time it takes to walk that distance is 50 seconds. So I can say that my average speed is distance over time. So it's going to be 120 divided by 50, which gives me an average speed here of 2.4 meters per second. Second question asks about the average velocity during this time, which is a similar calculation. The key difference, though, is we're now looking for our displacement here rather than our distance. And in order to get that, displacement is really the distance from where we start right here to where we end. So the length of that line is going to be our displacement. So we have to use some things we know about triangles to find that, but basically we are finding the hypotenuse of this triangle. And so in order to get that, I'm going to do a squared plus b squared is equal to c squared. And so I have 30 squared plus 90 squared equals c squared. That means that c squared is equal to 9,000. I take the square root of both sides, and I get that my hypotenuse here is 95 meters. Rounds to 95, it's not exactly 95. Now I can take that and sub that in to my chart here, so I know that this is 95 meters. My time is 50 seconds, and so I can go ahead and say that my average velocity here is going to be displacement over time. So it's going to be 95 over 50, which gives me an average velocity here of 1.9 meters. Again, meters per second. Again, that's rounded slightly, but that's a close enough answer there. All right, for this next one, we have one of those problems where there's multiple parts. In this case, we have Sophia driving 400 miles from Westchester down to Virginia Tech, and we know for the first 200 miles, she has an average speed of 70 miles an hour. So I'm going to go ahead and set up that first part, traveling at 70 miles per hour for a distance of 200 miles. Don't know the time, but we can find that. For the second part, we don't know the average speed for that second part. That's ultimately what we're looking for, but the distance would be the remaining 200 miles. We don't know the time either, but we do know for the total trip, all right, we have an average speed here of 60 miles an hour, all right, and we travel a distance of 400 miles. Don't know the time, but once again, we could find that. So what I'm going to do is, ultimately I am trying to find that average speed for the second part, but I'm not really worried about that right now. I'm just going to find what I can find, and what I can find is the 2 times. And both of those come from using the average speed is distance over time formula. So for this first part, we can say 70 is equal to 200 over t. Here's another case where we're looking for a variable on the bottom. So I'm going to cross multiply, put that over 1, and I end up with 70t is equal to 200. So my time for the first part ends up being 2.86 hours. I can do the exact same thing here for the total. All right, same formula, but now it's 60 is equal to 400 over t. Once again, I'm going to cross multiply by putting this over 1, and I'm left with 60t equals 400. And so that means my time for the overall trip is 6.67 hours. Well, I can put those two together here, and I can use that to figure out the time for the second part. I'm just going to do 6.67 minus the time for the first part, 2.86. I end up finding that the time for the second part is 3.81 hours. Once I have that, okay, I can go ahead and substitute that in, and I can solve for the average speed here for the second part, which is just going to be the distance of 200 divided by that time that I just found, 3.81, and so I end up getting an average speed here of 52.5 miles per hour. And that ends up being my final answer here, the average speed for the second half of the trip. All right, for this last one, on this page we have a description of a motion, and we need to draw both the position versus time and velocity versus time graphs that match it. So I'm just going to take this one part at a time here. So starting with this first motion, we're going to speed up on a unicycle from rest. All right, and so what does speeding up look like? Speeding up on a position graph means we're getting slopier, something like that. I'm going to show it in the positive direction, but you could, of course, show it in the negative. On the velocity graph, that just means a line going away from the x-axis and a line above the axis indicating that's positive. We're then going to slow down to a stop. So slowing down to a stop means we continue traveling in the positive direction, but our graph is going to be flattening out. Okay, something like that. On the velocity versus time graph, it means we're going back to zero, back to the x-axis. That's slowing down. Still positive, though, because we're still above the axis. We then remain at rest for a period of time. Okay, remaining at rest is going to be a horizontal line on my position graph. On my velocity graph, it means it's a line specifically on the axis. And then we began riding in the opposite direction, so we'll need to show a negative velocity at a constant speed. So on the position graph, opposite direction means we're going down, and constant means it's just a straight line, so something like that. On the velocity graph, it means we're below the axis, and it's going to be a horizontal line like that. That shows a constant speed. Moving on to this position versus time graph we have, the first question we're asked about is what is the velocity of the object at 1 second? And velocity on a position versus time graph is going to be the slope, so delta y over delta x. So I'm going to pick some points here. That first point is 0, 2, and then I have this point here, which is 2, 10, and I'm just going to find the slope using those points. So change in y, 10 minus 2, over the change in x, 2 minus 0. That gives me 8 over 2, which gives me a velocity of 4 meters per second. Next question was the acceleration at 1 second. I know that acceleration on a position graph is the concavity, and so I'm looking here at 1 second, and I notice that that line is perfectly straight. It has no concavity. It's not concave up, it's not concave down, and so that means my acceleration here is going to be 0. During what time intervals is the object not moving? On a position graph, not moving means 0 velocity, which translates into a slope of 0, meaning a horizontal line. So when does that occur? That occurs in this region right here, from 6 seconds all the way to 8 seconds. I have no slope, horizontal line, and so that means no velocity. Next, I want the average velocity over the entire 10 seconds. In order to get average velocity, what we need to do is set up my average velocity equation. So I'm looking for my displacement and my time. Displacement on a velocity versus time graph, I just need to think about my change in position. So I start here at a position of 2 meters and I end up here, which is a position of 14 meters, which means that my change in position is just going to be from 2 to 14, which is a change of 12 meters. So that's my displacement. The time that it takes for that to occur is 10 seconds, and so I find that my average velocity here is going to be 12 divided by 10, or 1.2 meters per second. All right, for the last part, we need to draw the velocity versus time graph that matches the given position versus time graph. All right, so I'm going to take my graph, I just moved it on down here, same graph from above, and I'm going to break it up into pieces. So for this first piece, what I see here is I have a constant positive velocity, so positive velocity, 0 acceleration, therefore it's constant. And I want to draw that my velocity versus time graph. That's just going to be a horizontal line above the axis, constant positive velocity. For the next part, I still have a positive velocity, but now I have a negative acceleration. I see that because it's concave down, and that means that I'm slowing down. And so that means this line here is going to go towards the axis, still above it because it's positive, but going to 0, indicating that we are slowing down. This next portion, okay, I have 0 velocity as well as 0 acceleration. This is just a case of not moving at all. And so the line's going to go along the axis for that period of time. And then for that last section, I have a negative velocity. All right, I have 0 acceleration because once again, it's a straight line, no concavity. And so this is just another case of constant. And so I want to show constant negative velocity, and that's just going to be a horizontal line below the axis. All right, for this velocity versus time graph, we have another series of questions. So first we want the velocity at 7 seconds. To do that, I'm going to look here at 7 seconds, which is right here. And all I need to do is go ahead and read the graph for that point. And I see that at 7 seconds, the value of my velocity is 6 meters per second, just reading the graph. Okay. Next, I want to know what is the acceleration at 10 seconds. So that would be this point right here. Acceleration on a velocity versus time graph is going to be the slope. So once again, I'm going to find the slope here. Now though, since it's a velocity graph, that slope represents acceleration. So I'm going to pick some points here. The first point I'm going to pick is this point up here, which is the point 9, 6. And then the second point I'm going to pick is this point here, which is the point 11, 0. So I'm going to find the slope using those 2 points there. So change in y over change in x. 0 minus 6 is my change in y over 11 minus 9, which gives me negative 6 over 2. So my slope, which is my acceleration, is going to be negative 3, and the units are meters per second squared. Next one, we want to know during what time interval or intervals is the object slowing down. The key on a velocity versus time graph is slowing down. It means that we are approaching the axis here. So anytime we're approaching the axis, that's going to be slowing down. So we have 2 points in time when that's true. The first is from this point here, and you can see our velocity goes from negative 6 all the way to 0 over the period of time there from 3 seconds to, or from 0 seconds to 3 seconds. All right, and then the other time when we're slowing down is going to be this period of time here. We see our velocity goes from 6 down to 0, and so that is going to be from 9 seconds to 11 seconds. All right, next question here asks about what is the overall displacement of the object, and for that we're going to be thinking about the area under the curve. So keep in mind that's always the area between the graph itself, okay, and the x-axis. So what I'm going to do is I'm going to divide up into 3 shapes. There's 1, that triangle, there's 2, that triangle, 3, that rectangle, and 4, that final triangle there. And we're going to find the area of each one of those shapes. So for that first shape there, it is a triangle, so the area is going to be 1/2 base times height. So that area will be 1/2, base is 3, height is negative 6. We do include the negative, it's below the axis, and we get an area there of negative 9 meters. Moving on to area 2, another triangle here. The base of that triangle there is going to be 3. The height is positive 6. So that gives us an area of positive 9 meters. We continue on to our rectangle, which has an area of just base times height. So the area is going to be base there of 3 and a height of 6. So that area ends up being 18 meters. And then we move on to our final area here, another triangle. So the base for that triangle is going to be 2, height is 6, and so that gives us an area of 6 meters. To get the total displacement, I'm just going to add all of these up. Negative 9 plus 9 plus 18 plus 6, and I end up getting a displacement here of 24 meters. Okay, for the last part here, I need to recreate the graph. So once again, I'm going to break it up into pieces. So there's my first part that shows on the velocity graph a negative velocity because we're below the axis, but a positive acceleration and slowing down. So I want to show a negative velocity, but I want to show positive acceleration, so concave up and slowing down. So that first part's going to look like that. Okay. The next part of the graph, we switch over to a positive velocity, still have a positive acceleration, now we're speeding up. So I'm going to continue having my graph be concave up for that positive acceleration, but now it's going to be going up. So that's what that first part of the graph, first and second part of the graph look like. I then have a positive velocity and 0 acceleration, just maintaining that constant. And so that's going to look like a straight line, something like that. And then for the final part, I still have a positive velocity, but now I have another negative acceleration and I'm slowing down. And so there I'm going to be flattening out.